Hi everyone, my name is Ross Rincioni, and I'm presenting today on the topic of 3D printing, bioprinting and organ production in healthcare. 3D printing has been receiving much attention for its potential across industries ranging from manufacturing to aerospace, food, and recently even the healthcare industry. It has been touted as the next big thing since the advent of the internet. Though the technology has its root dating back to the 1980s, it is recent that the technology is breaking out of research labs and becoming mainstream due to the evolution of the technology as well as printing materials. Just to give you a brief background of 3D printing has been a type of additive printing that was first visible in 1983. It was a manufacturing breakthrough as it radically changed the production ideology from subtractive manufacturing to additive printing. Subtractive manufacturing has been synonymous with being tool-dependent and resulting in 90% wastage of raw materials. This is a stark contrast to additive printing technology, in which a physical model is built by printing layer upon layer based on a 3D digital model. Known initially as rapid prototyping technology, it was designed as a fast and cost-effective method to produce prototypes. In recent years, due to the advancement of the numbers and types of additive printing procedures, the technology availed itself for various uses by the different industries. Thus, mainstream market, including small companies and even individuals, have soaked up the technology with much fervor. Furthermore, initially the technology was reserved for use by multinational companies due to the high cost of printer ownership. Accessibility of scaled-down printers at a fraction of the cost resulted in exponential adoption on all fronts. The 3D printing technology has by far established itself in many of the industries, proving increasingly to be indispensable. However, the medical fraternity is still a long way away from producing fully functional and made-to-order organs customized for individual patients, which is its ultimate goal. Presently, bioprinting is at a stage of producing tissues for pharmaceutical drug use mostly. However, the race to substantially maximize 3D printing capabilities has been intense since the early 2000s, with pioneers such as Dr. Otlo of Wake Forest University's Medical Center and the company Organovo working towards printing tissues that remain viable long enough to develop and live within human bodies. The medical market is expected to expand by 365% and $867 million by the year 2025. With greater innovations in commercial printers as well as custom designed printers by individual research institutions tailoring 3D printing manufacturing process to the medical market, the associated businesses could reach up to $6 billion in 10 years. A brief timeline is displayed on this slide to show the various changes in technology that have led up to where we are with bioprinting currently. Bioprinting is a long way from commercialization. However, they have been actively producing tissues for pharmaceutical drug testing, and there's currently a race to substantially maximize 3D printing that has been ongoing since the year 2000. As mentioned previously, it is expected that the market's going to expand by 365% to $867 million by the year 2025. The loss of tissue due to trauma or cancer has often led people partially disfigured. Some areas of tissue can be replaced by skin grafts, a procedure of removing tissue from one point of the body and transplanting it to another area. This procedure has the obvious shortcoming that it is necessary to have a donor region. Another setback in that is that this procedure is limited to simple structures such as skin, bone, and some connective tissues. When trauma or cancer leaves a person without an ear or nose, grafting is almost impossible to use. Although the nose and ear seem like simple structures to recreate, cartilage is often difficult to grow due to constraints in blood flow that ultimately cannot support cell life. Instead of living tissue replacements, such as with grafts, ear replacement has been dominated by the use of prosthetics. Ear prosthetics have come a long way since they were first developed. Silicone replacements have been popular, but still fail to look realistic in some situations. Very recently, this issue has been addressed with the ability to scan 3D images and print them using a 3D printer. A 3D printer is now capable of printing an exact opposite match of a patient's ear to replace a missing one. The printed ear is attached using glue or by a magnet. It has been suggested that in the near future, this prosthesis procedure could take as little as a few years from the scanning of an ear to completely printed prosthetic ear. To address the limitations of silicone prosthetics, recent bioprinting has forged a new path towards ear replacement. The end goal of ear replacement bioprinting is to be able to 3D print an exact copy of a patient's ear using living tissue that can be surgically attached to the patient, a perfect replacement ear that interacts with the body like a normally grown ear. As discussed previously, the main difficulty with ears has to do with the tissue that comprises an ear, cartilage. Cartilage is often difficult to grow because of the blood flow problems. A research team at Morrison Hospital in Swansea, Wales, has come up with a solution to this problem that results in a viable replacement ear that is grown from a patient's own cartilage. This method consists of a multi-step process that approximately takes 2 months to produce. First, a small sample of cartilage is taken from the patient. It's usually sourced from a knee or a finger. Then the cartilage is put into an incubator to multiply the cells, leading to the growth of cartilage tissue. Next, the newly grown cartilage is combined with a liquid formula to create a jelly-like product. This product is then used with a 3D printer to print along the ear with a 3D scan of the patient's ear. The 3D printed ear is then transferred back to the incubator and combined with reagents and nutrients to encourage the cells to grow their own cartilage. The resulting ear is planned to be implemented into a patient, although the research has not yet reached this point. As previously discussed, there are methods of artificial ear replacements that are produced by using some of the patient's cartilage along with an incubation method to grow higher amounts of cartilage needed for the replication of the ear. However, this is not the most advanced application of 3D printing ears that is currently available. The most advanced methods use cells that are sourced from other animals along with 3D printing to replicate the ear. A team has produced a method of 3D printing that uses cells sourced from animal donors along with biotin and streptavidin to create a structure that doesn't rely on scaffolding to remain structurally stable when printing complex structures such as the human ear. Research teams at Wallenberg Wood Science Center have made further improvements. They have successfully printed an ear in a method similar to that of the previous team, but have also shown that the ear can survive in mammalian tissues. They implanted the ear within living mice and witnessed sustained cartilage growth. They also discovered that an increase in cartilage production occurred when stem cells from bone marrow were introduced to the ear's environment. The current forerunner in artificial ear production utilizing 3D printing was developed at the Wake Forest Baptist Medical Center with their integrated tissue and organ printing system. They have developed a method that uses water-based gels that contain cells along with biodegradable polymers arranged in a lattice to create ear structures that can be implemented in living hosts for growth. The technique they developed to address cartilage blood supply issues comes in the form of microchannels. These microchannels allow the diffusion of nutrients to the 3D printed cells of the ear structure. The 3D printed ear they implanted in a mouse vascularized in as little as a month. To further demonstrate the ability of their 3D printing method's effectiveness, the team printed muscle tissue and jawbone fragments to implement in mice also. The muscle tissue vascularized and showed nerve formation within 2 weeks of the implant. The bone fragment showed vascularization within 5 months of the implant. Moving beyond ear prosthetic creation and fully functional ear creation using 3D bioprinting, the healthcare industry ultimately desires to be able to create fully functioning organs for use in transplantation with patients who need transplants. As the area of 3D printing continues to grow, more and more questions are going to be raised. The idea of ethics is always raised when it comes to using human material. Will it be that people will start to patent their DNA to be used in 3D printing, or will people find it odd to be printing live materials? Along with that, the question of cost is always thrown into the mix. The prices of equipment are quite substantial now. However, they are moving in the downward direction as newer technology comes out and cheaper materials are produced for use in 3D printing. But who would take care of the cost of repairs and the cost to print particular organs? What or who will decide the pricing once 3D printing begins to make the breakthrough that people are looking for? Which then brings up, who will be in charge of quality control? Will hospitals have to take on the cost of making sure that the products that are being printed are up to a particular standard? Where will these 3D printed organs come from, and what will be the determining factor to make sure that they are the real deal and not counterfeit organs? Other concerns deal with the delicate nature of ethics. If genetic material is sourced from a patient and successfully used to recreate organs, who becomes the owner of that genetic material? There have been issues in the past of using genetic material of people without their knowledge, such as in the case with Henrietta Lacks' cancerous cells, which are still in labs to this day. Other issues exist as well. Will there be patents on new types of printing processes? Or will there be patents on specific organs? Finally, there's the question of who's responsible for a failed organ transplant. If the organ does fail, is it the hospital's fault or is it the manufacturer of the organ's fault? What will be the legal implications of these faults? The unpredictable future of 3D printed organs is only overshadowed by the uncertain regulations and patents to follow. The regulatory boards around the world are being outpaced by an exponential speed of innovation regarding the possible applications, advancements, acceptance, and consequences of this technology. Also, bioprinted products blur the traditional chain of sale concept. Thus, warranty along with liability becomes a contending issue that will demand clarity before mass production of 3D organs in the future. Finally, with healthcare already dealing with the burgeoning cost of giving care to the population, it is unlikely that the Centers for Medicare and Medicaid Services or insurance providers will pick up the burden of these expenses associated with it unless these medical procedures become approved and are considerably cheaper than traditional treatment methods. At this point, I'd like to thank you for listening to my presentation. I hope it is going to provoke some interesting discussion within the discussion boards, and I look forward to answering any questions that you have. Thank you.